Good morning, everyone. I know you're here today to hear about how Call of Duty uses machine learning to personalize player engagement. And we're going to get into the details of that. But first, I want to tell you how we got here. Just like many of you in the audience, we have a product. In our case, our product is a video game, Call of Duty. And our product has a lot of unique features. Our game studios spend months building those features, and we are very excited to talk about them. But first, we have to figure out what we want to talk about. And in the past, it might have gone something like this: a group of people sitting around a table, and someone says, you know what, we should talk about multiplayer. Players like playing together, and we've got some cool stuff this year. And people will nod their head, and then another group or another person at the table will say, you know what, but we should talk about zombies. Players love killing zombies. We need to make sure we include that. And then somebody else will raise their hand and say, don't forget, this year we have a new game mode. It's called Blackout. And this is our take on Battle Royale. Everybody's going to want to hear about that. And this will go on and on for some time. People talking about the different features in the game, trying to figure out what to focus on, until somebody asks that question. Okay, what are we going to talk about? What should we focus on? With so many features in our game, the correct answer is all of it. Our game studios build games to be inclusive. They want everybody to find something to enjoy in our game, just like you want your customers to find something that they connect to in your product. So how do we do that? Well, if we were a small gaming company, maybe we had 100 players, we could go to each one of them, we could ask them questions about what's important to them, what they're looking for in a game, and tell them how our product matches their expectations. Unfortunately, that doesn't scale. We needed a solution that's going to work for millions and millions of players. So how do we do that? That was with personalization. First, we started with rules. We would say, if you play multiplayer, we're going to talk to you about multiplayer. If you play zombies, you like hunting zombies, we're going to talk to you about zombies. And then we moved to machine learning. And today, we're going to talk to you about how you can use machine learning to drive personalization to connect your customers to features in your product. So first, let me just introduce ourselves. So we are with Activision, as you all know, mentioned already, we make video games. I am Gina Hope. I lead the consumer technology team. With me today is Mike Blesky. He leads our DevOps in infrastructure, and Diego Toledo, one of our software architects. So what is consumer technology? Let me be clear. We don't build games. We've got game studios to do that. Our job is to elevate those features and that content in the games and connect it to the players, finding those things that are most relevant to the player regardless of what channel they're in. That might be on one of our websites. That might be through in-game messaging. Could be in our mobile companion experience or in a voice skill. I've talked a little bit about features and connecting into players, but let's first take a glimpse at what those features might look like in our game. So here's a quick peek at Call of Duty Modern Warfare.
The rules of engagement have changed.
As you can see, there's a lot to talk about in that game. A lot of features and a lot of different things that we could focus on. So how are we going to find the right feature for the right player? And how are we going to implement this machine learning approach for our players? Well, first we asked ourselves the question, what are we trying to solve for? What is our goal? What are our goals with this application? So we came up with a few. First, it's to deliver the right message to the right player at the right time and the right channel. We want to make sure that our players are playing the things in the game that they love, but we're also telling them about new areas that they may not have considered, something else that they may be interested in. We want to make sure that we're listening to the players. It's not good enough for us to make assumptions or go with our gut about what the players want to hear. We need to make sure we're taking their feedback seriously. We also need to do this while maintaining cost. And then finally, a system like this can be very complex and unwieldy. So we need to make sure whatever our solution is, we have a plan to handle it. So our solution focuses on 3 things. 1, less human intervention. Stop letting people define rules to choose what players want to see. And I'll tell you, this was probably the hardest for most people to give up. This means we can no longer go with our gut on what we think is important. We're letting the machine choose for us. And if we're going to let the machine choose, we need to give it lots of options. We need to have a variety of messages, different layouts, and channels. I may like a lot of text. Somebody else may want to see it visually. This person over here wants a video. And then we need to make sure we're continuously learning. We don't build it and set it and forget it. We constantly look at the model and see, is there a better way? Is there something we can tune to do differently? Are there better messages that we could be choosing? And now Diego is going to actually take us through the details of what that model looks like.
Okay, so let's talk about our machine learning solution. So what we're asking ourselves is, what is the best next message? This is really important, because what is the best next message that is going to lead to long-term engagement? Think that you guys might have teams that come to you and ask, okay, we need to increase engagement, we need to increase revenue, or we need to increase visibility for a specific game feature, and now you're juggling all those balls in the air, and you have like a finite amount of real estate inside of the game, right? So how do you deal with all of that? And you also sometimes want to make suggestions to the user. Try this different game mode, try this weapon, buy this new item. When is the right time to approach the user and make those suggestions? And the game is always evolving. And a message that is talking about a specific game feature in the past might become really relevant again because this new feature got revamped now, and now this old message needs to reprioritize. How do you go back and reprioritize things dynamically? Or maybe this other feature is broken, and we need to deprioritize this really fast. How do we deal with that in real time? So for people that worked with live products, this curve is really familiar. So you have early engagement building up, and there's a peak, and eventually there's a tail. Now, different people are going to have different shapes. Some people are going to have like a higher peak, lower peak, shorter tail, longer tail, but that's what the average curve looks like. Now, another way to look into this curve is, this is your Call of Duty journey. Every part in this curve is what you were doing at that specific time. So every point in this red line is your state in your journey. So here, in the beginning, you are learning about a specific game feature. You're learning that you like this game mode. You learn that you like this other game mode even better. This is your preferred weapon. And it goes up, up, up. And then you start playing less and less and less and less. Now, different people have different shapes. But those shapes might overlap. And when those shapes overlap, we have people sharing states for a moment in time. So I can look at somebody that was in your state that you are right now, but this person was 6 months ago, and see what happened to this person. Did this person increase engagement, decrease engagement? What message this person was sent? And was it good, was it bad? Now, I get all this information, and I can make a decision about what to do with you right now. And this is really powerful because everybody, very different players, are helping each other, and we're going to have like a better product because of this. Now, the way we achieve that is through reinforcement learning. This is a textbook example of how classic reinforcement learning works. So I'm going to go really fast so you guys have like some background how everything was done. So in this grid, and generally you have like a reward state, which is the 1.0 on the top. And sometimes you have like a negative reward state, which for you could be the churn state. You want to avoid the state. And in reinforcement learning, what we're doing is we're trying to find the value of those other cells. Those other cells are specific states that exist in this world. And in this specific world, we have 4 actions. You can go up, down, right, and left. And we're trying to learn what is the value of taking this action in the specific state. What is going to give you that? So when you solve the world using reinforcement learning, you get something like this. You see that going up in different states have different returns, but if I drop you anywhere in this grid, you know where to go to find a reward. Now, how does it translate to Call of Duty? States for us is user attributes. So anything about engagement, revenue, preferred items, inventory, everything comes down to build your state. Every circle you see in the screen, it's a state. So the X's are churn states. The blues and the greens are states that I'm going to talk about it. But the arrows here are different because remember the arrows are the actions. It's how I walk from one state to the other. And messages are pretty much what we send to the user. So if I want to move a user from state 1 to state 2, I send him a message. Hey, do this in the game. Hey, try that. Hey, did you hear about this new game event? And by doing that, I change your state. I send it to another state. And some states are better than others. So a quick example. Let's imagine that somebody comes to you and say, hey, let's make everybody play zombies. Now, state 1, in this case, could be a state that is the user is a beginner, doesn't know much about Call of Duty, doesn't know how to find its way around the game. If we introduce this feature really early, it can lead to a low engaging state, which we see going down from S1. Now, what our model does is it's going to look ahead in the future and see, is there a better place that I can introduce this feature that is going to lead to a higher engagement? So in this, you can see there's a path. I need to reroute user to state 2 and state 3, and there, if I send him the same message, it's going to lead to higher engagement. Now, there's a risk. In state 2, the user can churn. You could churn from any state, actually. Now, how confident am I, the model, that I'm going to be able to avoid this state, and I'm going to make people go to state 3 in order to experience this feature? As long as I have a higher confidence, I'm going to do this rerouting. If I have a lower confidence, it's going to do something different. Now, messages are our arrows here. And we do have seasonal content, and we have evergreen content. Every time somebody adds a new message in the system, what you're doing, you're creating new arrows. So if the arrow that takes you from state 1 to state 2 is a seasonal content, a seasonal message that's going to be taken down tonight, that street got closed. You cannot send users there anymore. So this changed the whole strategy. And we're able to adapt that in real time. But you can do the other way around, too. I can go to somebody that generates content and says, hey, we should focus on taking people from state 1 and state 3. We should craft a message specific for that. So we can avoid the states 2 and avoid the churn state. you probably start to realize that our actually problem is much more complicated than the classic reinforcement learning problem, because we have so many states. We actually have hundreds of thousands of states to explore. And we were learning in that previous example the value of taking an action in a specific state. And when you have like hundreds of messages and hundreds of thousands of states, there's no way you can explore all those pairs and learn the value of each one of them. It's too much stuff to explore. And as the game evolves, we have new states getting created. So for example, if you had a new feature, a new game mode, or something different that we want to track about the user, this translates to new green cells being popped into existence. And things get way more complicated now, because now you have all those new states to be tracked. And the same thing for message, like I said before, messages are being created, deleted, removed, and edited all the time. And this changed the effectiveness of the message too. This is how, this is the very center of the graph. We cannot fit all the hundreds of thousands of states here, but this is the really beginning. The lighter the color is, the more engaged the user is with Call of Duty. The size of the circles there is how many people are in that specific state. So you can see already some patterns that some states are connected to some other states. And this is really powerful now, because I can give a heads up before somebody goes to like a critical churn state 1 week before. You can run simulations to see where people are going to be 1 week from now, 1 month from now, because we are learning here like how the world is connected and how user experience your game in the long term. So in the very center, you see a larger circle, and this is the root state. When you start playing Call of Duty, that's where you start. Now, because it's really dark, now it's dark because you start a game, we don't know anything about you. So everything about you is 0. So that's why it's a dark color there. But you see all those possible directions to go. There's all those possible futures for you to explore, and all those possible paths, and where they send you to. Here you can see it's clear that there's like a cluster with light circles on the bottom. You want to reroute users there. So that's the strategy that the graph is going to do. Okay, so it's really complicated because users could be in any state, and they have all those dynamic factors that I talked before. How do we navigate that? How do we find which state I want to send the user to? What is the best path for me to send the user? What we use is Monte-Carlo tree search. Monte-Carlo tree search really helps us with that, because we don't have to come up with like a player model. Like we don't have to come and say, here how the player is going to behave, here's how players think, here how messages work, this message is going to be tagged with that. We don't have to do any of that, because we're going to approximate the word through sampling. And the more we sample, the closer we get to the real world. And we have enough traffic in Call of Duty, so we can actually approximate a very good model in a couple of hours. And this is designed for a big search space. You guys are probably thinking, oh, you guys have like so many different paths, so many different states. Monte-Carlo tree search really can deal with that. If you guys are familiar with AlphaGo, their search space was much bigger than our search space. So I'm not at all worried about the number of states that we have. And this deals well with noise. In noise, it's important because you're sending marketing content to the users, and not necessarily somebody did something because you told them to do it. Maybe their friend called them to do it. Maybe they saw an ad on YouTube, and they did that all along. Now, we need to be able to account for all this noise in the system and maybe make a U-turn about something that we just learned that was like a statistical fluke all along. Here's a quick review how Monte-Carlo tree search works. So we have those 4 distinct phases: selection, expansion, simulation, backpropagation. So in selection, you're in a state, and then we're going to look ahead and see where do you want to send this user to. So this is the path that we're navigating. Some paths are better than other paths, and so we're going to explore only the good paths. Eventually, you're going to reach a state that you don't know much about it. There's a leaf node, and that's where you're going to have the expansion and simulation comes in, because you want to know what happens when I do something in the leaf node. And backpropagation is the backpropagation of this value all the way up to the root. Now, you're going to propagate a +1, a -1. You're going to propagate a signal that next time you're in that situation, they need to choose, you're in this state again, you need to choose a message. You know that you should explore this path or not. Now, look on the backpropagation side. You see that one side of the tree is being explored more than the other side of the tree. This is by design because remember that we don't want to explore every single part of the tree. It's just not feasible. So we're only looking for promising areas of the graph. But we could have an example that we have like an early reward of +1, +1, +1, which makes us explore one side of the tree more than the other. But if we were to avoid and explore 3 levels of no reward, probably there was like a +100 there somewhere. So we need to balance this exploration and exploitation. And this is the formula, the standard formula for Monte-Carlo tree search for exploration and exploitation. So in one side, you see in the left side, that's the reward. So this is how much I know about the subtree. This is how much I know about this path. I collected this reward. I collected this signal. I know that if I go here again, I'm going to get this reward. The other side is the interesting side, but what you need to focus here is the big N and the small n. The big N is every time my parent node was in a situation they had to choose between me and my sibling nodes, how many times my parent was in the situation. Every time this happens, you get a +1 on big N. The small n is every time I got selected when that situation happened. So what's happening here? Every time I got selected, the small n grows. If the denominator grows, the fraction gets smaller and smaller, so it translates to that I become less attractive for next time I'm being looked into. And because I'm becoming less attractive, my sibling nodes are becoming more attractive because their small n stays the same because I'm being selected all the time, and their small n is just growing. Their numerator is growing, 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 growing. So they're becoming way more attractive now for the parent node. Select. Now, eventually, you're going to collect enough information. You know that there's no hope, this path is not good. You're going to get out of this up and down, up and down, up and down. You just want to converge to like an optimal path. That's what the log is doing here in the square root. This is just going to cap the value. So it's not going to grow much more than a certain number. And so in the end, after you explore enough times, the exploitation value is just going to dominate this side of the equation. Now, you might have a product, a business case that you do need to favor a little bit more or even much less exploration because maybe there's a penalty for you to exploring too much. Or maybe there's no penalty for you to explore. So that's the C, that's the constant, and you just play with C. There's a hyperparameter, and you choose bigger, smaller C's just to tune how much you want the model to explore. Now, until now, we talked about how to choose the next state. I'm in state 1. Should I go to state 2, or should I go to state 4? So this is, we know how to do that. We're going to look at the backpropagation values, and we see which states are better than other states. Now, how do I get to state 2? Remember, we need to choose a message. We have a huge catalog of messages to choose from, and showing a message to a user not necessarily is going to take to the state 2. Maybe it's going to take to state 5 or state 10, and some messages are better than others to take to state 2, which is the one I want to do. Now, remember that we don't have a deterministic outcome. Not necessarily because I showed you this message and you move state, it was because of me. And sometimes I need to show you the same message 100 times for this message to take effect. And the value might change over time because something is really hot now. There's a lot of buzz around this new feature. So this message is really affecting moving people to the specific state. But later, the buzz goes down. So this message effectiveness goes down. So we need to be able to dynamically adapt to all those fluctuations. So we're running an attribution model. Every time a user sees a message, we send to Kinesis Analytics. And every time a user changes states, we send to Kinesis Analytics. So we have those two tables. This is very simplified. Event table, you can think of like a state change event. And what we're going to do here, we're going to join by user IDs and timestamp. So we have this event ID there, and the event just happened. Now we're going to look through a window of time before this event happened. X minutes, X hours, X days, whatever makes sense for you, and see all the content the user saw before changing states. And then I'm going to attribute the state change to that specific messages. So most of the time are going to be multiple messages. But most of the times, what is going to happen is the dark gray. And the dark gray is you're going to see a message, nothing happens. This translates to a self loop in the graph. And those are our successes and our failures. And later, those successes and failures we're going to be used to determine how effective this message is in sending to a specific state. And from here, that's how the whole tree, how the whole graph gets built. Now, we're all in Vegas, right? So Thompson sampling is going to help us find the true value of the message. And Thompson sampling is something that it was originally taught for slot machines in Vegas. And just let's think about an example right now that I come to you and say, we're going to play tonight slot machines, and we're going to try to make as much money as we can, but we only have one night, finite horizon, very important. And the second piece of information is different slot machines have different payouts. So what we're doing here is we need to play in a bunch of slot machines, try to approximate what is the real payout of those machines, and then for the rest of the night, only play that machine. So what we're doing here is the trial. The trial is every time the server was asked, give me a message for this user, and the server is going to see what's the best message, and it's going to learn. So in the beginning, you don't know much about what's the true value of those messages. On the top, you'll see the true value because you can go back in time and aggregate everything nicely, but at the time, we did not know. So every message is being explored equally, but you see that very fast. For example, number 3, we learned that message is crap. We cannot use that message anymore. So it just stopped exploring that message. So you can think of this as like a A/B test on steroids that we're shutting down bad variants on the fly, and we just double down resources on good variants. You see that green really is getting a lot of the traffic there, but we do still explore some of the other message, because remember, that could be a statistical fluke. It could just be living in a universe that you get 100 heads in a row, but the coin happens to be fair, so you need to always be able to make a sanity check. This is the same from before. Now, we're just taking different snapshots at different trial numbers. In the beginning, you don't know anything about any message. So any message has an equal probability between 0 and 100 from making a transition. So it's the same as random. Every message is random. Now, as some feedback start to come back, you start to see that you start to learn some curves here. You start to see that some probabilities. And very fast, you see green moving to the right and get skinnier and taller. So what happens here is that green is skinny and tall because we're only learning about the true value of that message, and we're only putting resources there. We're getting more confident about how good is this message. We're learning the value. Now, some other messages have like a very wide curve. And this curve is because we're not really certain about the true value of this message.
Check.
But we know that in the best case scenario, it's never going to be as good as green in the worst case scenario. So we don't have to spend any more resources playing in this bad slot machine. We only want to play in the good slot machines. And here's the final product. This is how we find the best next message to the user. This is a screenshot from the game. This is the message that got selected to a user. So this is from Black Ops 4, last year's game. And we learned what are the best messages for this user. So the top message is to showcase next year's game, which is this year's game's Modern Warfare. And we have 2 engagement messages right after, and we have like a sales message after this.